Have you ever wondered what the hell time really is? I'm asking seriously. You and I both live in it, get swept along by it, are limited by it, yet we accept it as something completely obvious. People often tell each other that time slows down near a black hole, as if it's some amusing science anecdote to share at dinner. But let me tell you something far stranger. If time did not slow down near a black hole, this universe, the very universe you're sitting in right now, listening to me, couldn't exist for even a single second. No galaxies, no light, no planets, and certainly no you to wonder about it. This isn't because black holes eat time, or because the universe likes to mess with us. There's no magic here at all. It all comes from a deeper, more beautiful reason. And if you give me a few minutes, I promise you'll feel it. Not just understand it with words. And the best part, you don't need to know anything about tensors, metrics, or Einstein's long-winded equations. You only need one thing: curiosity, the greatest gift, in my opinion, that humans possess. Today I want you and me to go on a journey together to discover why time dilation isn't just some weird effect that appears near black holes. It's an essential component for the universe to function at all. Without it, everything falls apart. With it, everything becomes miraculously sensible. So if you're ready to leave your familiar intuition behind, the intuition that sometimes makes us completely misunderstand the very world we live in, then step through this door with me to understand why time can stretch, slow down, or be bent. We have to go back to the starting point of this revolution. Einstein, and the simple but explosively powerful question he asked. When he asked, "What is gravity really?" he was challenging a conception that had dominated for 238 years since Newton published the Principia in 1687. Newton described gravity as an attractive force between two objects, and that model was excellent in countless situations. But by the early 20th century, small discrepancies began leaking through the cracks in the system, like Mercury's orbit deviating by 43 arc-seconds per century from what was predicted. To Einstein, those tiny numbers were the universe whispering, "There's something deeper here." In 1907, while working at the patent office in Bern, Einstein suddenly had what he called the happiest thought of my life. A person in free fall does not feel their own weight. And from that seemingly simple observation, he discovered a marvelous truth. Gravitation and acceleration are, from the point of experience, completely indistinguishable. You're standing inside a closed elevator, floating in space. No earth, no sun, nothing pulling you down. Suddenly, the elevator accelerates upward at 9.8 m/s question, exactly the familiar gravitational acceleration of Earth. What happens? You feel heavy. Your feet are pressed against the floor. Your knees feel slightly strained. Your body reacts exactly as if you were standing at home. There is no attractive force at all. Only the floor accelerating toward you. Now the opposite case. The elevator is in free fall. You float gently, just like astronauts on the ISS, even though the ISS still experiences about 90% of Earth's gravitational pull. They are weightless, not because there is no gravity, but because they are continuously falling around the planet. From this, Einstein reached a bold conclusion. The feeling of weight is not because you are being pulled down, it's because you are being pushed up. Gravity is not a mysterious pulling force. It is the state of a reference frame that is accelerating or in which space-time is curved. And to solidify this view, just 4 years after publishing general relativity in 1915, the 1919 solar eclipse observation showed starlight bending by 1.75 arc-seconds, exactly as Einstein predicted, and completely unlike Newton's prediction. From that moment on, gravity was no longer a pulling force. It became the geometry of the universe. Have you ever ridden a merry-go-round at the park? If so, congratulations. You've already participated in one of the cheapest physics laboratories on the planet. No blackboard, no tensors, no meter-long equations, just a spinning chair and a bit of angular velocity, and your body immediately experiences what Einstein spent a lifetime generalizing. Every time the ride speeds up, you feel thrown outward. But there is no mysterious force. Your body is simply trying to go straight, while the seat keeps forcing you to change direction. And right there, we begin to see how rotational motion can simulate gravity. And from here, our journey into the rotating spaceship model becomes completely natural. And to maintain circular motion, there must be a centripetal force pushing you inward. The feeling of being pulled outward is just your inertia resisting the change in direction. Exactly like how we once thought gravity was a downward pull, but in reality, it's the floor pushing us upward. To think about this idea more deeply, imagine a gigantic rotating spacecraft shaped like a wheel, like the space station designs proposed in the 1960s. The ship rotates steadily around its center. Suppose the circumference of the wheel is 300 meters. If the ship completes one rotation in 10 seconds, then a person standing at the rim moves at about 30 meters per second. Meanwhile, a person standing near the center only moves a few meters in the same time. Both are on the same ship, but their linear speeds differ dramatically. And here's the fascinating part. The person at the rim feels heavy. They are pressed against the wall of the ship, as if gravity is pulling them down toward an invisible planet. The farther from the center, the greater the weight they feel. Conversely, someone standing right at the center feels almost nothing because their speed is nearly zero. You might think, is that all? But we're not done. For Einstein, the issue wasn't just the feeling of heaviness or lightness. It was time. Recall the photon clock we mentioned. The one that measures time by the distance light has to travel. If the ship spins faster, especially at the rim, the photon has to travel a longer path between two fixed points, because those points are moving rapidly in the tangential direction. The time needed to complete one tick becomes longer, and because the speed of light never changes, never slows down to help you, the only possible result is clocks at the rim run slower. The closer to the center, the faster the clocks run. This creates a strange but beautiful effect. Standing on the same ship, two people at different positions live at different rates of time. Imagine two people on the ship, Anna at the rim, Ben near the center. Anna looks at Ben's clock and sees it running faster. Ben looks at Anna's clock and sees it running slower. But when each looks at their own clock, it appears to work perfectly normally. Neither feels they are aging slower or aging faster. This is the very spirit of relativity. Each person lives in their own time, and no one is wrong. If we crank the rotation speed to the extreme, say the wheel completes a rotation in less than a second, then the person at the rim will feel artificial gravity far greater than 1g. We could create 2g, 3g, even 10g if the ship spins fast enough. But Anna's clock would then run significantly slower than Ben's. The stronger the gravity, the slower the time. This is the artificial gravity generator that generations of engineers have dreamed of, and at the same time, the perfect intuitive tool for understanding real gravity. If you pay attention, this model almost perfectly recreates what happens in strong gravitational fields, like near the surface of a white dwarf or neutron star, where orbital speeds and space-time curvature are extreme. The person at the rim is like someone deep in a gravitational well, with time slowed down. The person at the center is like someone far from the gravitational fields, where time flows faster. And just like on the ship, each person sees their own time as normal. See, with just one rotating wheel, we've rebuilt Einstein's intuition. Acceleration creates the feeling of gravity, and velocity slows time. The rotating model isn't just a carnival ride. It's a small but profound replica of the real universe. At this point, you're probably wondering, if gravity is really just the ground continuously accelerating upward at 1g, doesn't that mean every point on Earth is accelerating at the same time, and therefore Earth should swell up or crack open like an overinflated balloon? This is a completely natural reaction because the geometric intuition we use every day is built on flat Euclidean geometry, the geometry that appeared more than 2,300 years ago with Euclid and has dominated the way we see the world for millennia. But let me be direct. Flat intuition works very poorly in a curved universe. When you imagine every point on Earth accelerating upward, you're picturing the entire surface of Earth like a flat plane where parallel lines stay parallel forever, and the distance between 2 points must change if they accelerate in the same direction. But Earth isn't flat. Its radius is about 6,371 kilometers, and that curvature is large enough to completely collapse Euclidean intuition in serious gravity problems. To see how far flat intuition leads us astray, recall the earlier example, a wheel with a 30-meter circumference rotating steadily with a 2-second period. Every point on the wheel is experiencing centripetal acceleration of about 15 m solid credit, greater than Earth's 1g. But what happens to the distance between 2 points on the wheel? It doesn't change at all. Even though every point is under continuous acceleration, the 5-meter distance between them remains 5 meters. No swelling, no breaking, no weird expansion. Why? Because they exist in circular geometry, not flat geometry. This is the first clue. Acceleration does not necessarily mean distances must change. The problem lies in the underlying geometry, not in the acceleration itself. Now apply this to Earth. 2 people stand 100 meters apart on the ground. If you use flat intuition, you'd think if the ground accelerates upward at 1g, those 2 people should move farther apart over time. But in reality, their distance remains 100 meters as normal. Why? Because they are standing on a sphere, and the straight vertical lines they imagine are actually geodesics curving toward each other. When every point on Earth accelerates upward, in Einstein's sense, that acceleration is directed along the normal to the sphere, not along parallel lines in flat space. That's why Earth doesn't swell up like an overinflated balloon. The curvature of the surface and its geometric structure determine how points respond to acceleration. If this sounds abstract, remember that even light traveling at 299,792,458 m/s is bent by space-time curvature. In the 1919 observation, starlight was deflected by 1.75 arcseconds when passing near the sun, exactly as Einstein predicted. This proves that space around massive objects is not flat, and therefore you cannot use flat intuition to reason about how acceleration affects distances. Here is the full English-American translation of the provided content, translated completely and accurately, without adding or omitting anything. To understand why time can be stretched simply because space-time is curved, we need a particularly important intuitive tool, the photon clock, a clock that operates using the fastest thing in the universe, light itself. Imagine an extremely simple device consisting of 2 parallel mirrors placed a fixed distance apart, say 30 centimeters. A photon is emitted from the bottom, shoots up to the top mirror, reflects down to the bottom mirror, then shoots up again. And every time the photon hits a mirror, the clock ticks once. That's all. The round-trip distance each time is 60 centimeters. And since the photon always travels at the constant speed of 299,792,458 m/s, The time between two ticks is determined entirely by the distance the photon must travel. This is the simplest, most beautiful, and most honest clock that physics can imagine. And it has one crucial feature. It cannot cheat. It cannot run faster or slower, depending on mood. It is forced to obey the speed of light, one of the strictest laws of the universe. Now place this photon clock inside a frame, moving horizontally at a significant speed. Say the ship is flying at 0.5 c horizontally. What happens? The photon still tries to go up and down as before, but while the photon is traveling, the entire clock is also being dragged sideways. Therefore, the path of the photon is no longer vertical. It follows a diagonal path, just like when you try to jump straight up while standing on a moving bus, but land slightly behind, because the bus is moving. The distance the photon must travel from the bottom mirror to the top mirror is now no longer 30 centimeters vertically, but a longer path, exactly according to the Pythagorean theorem. And because the speed of light cannot increase to compensate, the photon takes longer to complete one tick. That means the clock runs slower, not because the clock mechanism is broken, not because matter is affected, but because light must obey the invariance principle. Its speed is always c, no matter who is observing, and no matter what the frame of motion is. This is the foundation of time dilation in special relativity, but that's only half the story. Now see what happens when the photon clock is at rest, but the space-time beneath it is curved by mass, for example, near a large planet. When space-time is curved, the path that the photon must travel between the two mirrors also changes. But this time the change is not because the clock is moving, but because the space-time around the clock is bent in such a way that the straight line of the photon is no longer straight. It has to follow a longer path when near the planet's surface compared to when farther away, where space-time is less curved. And light cannot speed up to compensate for this longer path. It still has to travel at exactly c. The consequence: time near the planet flows more slowly than time farther away. Imagine two identical photon clocks, one placed at the foot of a mountain, one placed at the top of a 3,000 meter high mountain. If you let them run for 1 year and compare, the clock on the mountaintop will have advanced a few nanoseconds more than the clock at the foot of the mountain. This is no longer theory. Experiments with extremely precise atomic clocks from the 1970s to the present, such as the Hafele Keating experiment in 1971, when 2 atomic clocks flew around the Earth on airplanes, have all confirmed that clocks moving fast or in weaker gravitational fields run faster, exactly as Einstein predicted. Another experiment at the University of Colorado in 2010 showed that simply raising an atomic clock by 33 centimeters caused it to run faster by about 4 cots 10^104 seconds compared to a clock placed lower. These extremely tiny numbers, though hard to feel, are clear proof the photon clock is the absolutely honest foundation of time, and anything that affects the distance light can travel also affects the rate at which time flows. When you look at the photon clock, you see at the root what Einstein wanted to say. Time is not the ticking of a clock hand, but the distance that light must travel. It's not that your clock is wrong, not that matter is broken, but that the universe is playing by the rules. Those rules say that light always travels at speed c in all circumstances. If you force light to take a detour, time will bend accordingly to comply. And that is precisely why, where gravity is strong, such as near the surface of a neutron star, where the density of matter is 10^100 times that of water, time flows much more slowly than in a place with deep weightlessness. The photon clock doesn't care whether the object is big or small, beautiful or ugly. classical or quantum. It only cares whether the distance light must travel changes, and if it changes, time changes. That is the very foundation of every time dilation effect in the universe. In fast motion, the photon travels a diagonal path. In strong gravity, the photon travels a curved path. Both lead to one single conclusion. Time is not a constant. It is elastic like rubber, stretched or compressed, depending on the geometry that light must cross. The ship has a radius of 100 meters, spinning fast enough for a person at the rim to feel an acceleration of 1g, corresponding to a speed of about 31 m/s. A person at the center is almost stationary because linear speed decreases as you approach the rotation center. Give each person on the ship an identical photon clock. When they turn on the clocks, something strange immediately happens. Clocks at different positions run at different rates. The reason is not in the clock mechanism, but in the path of the photon. At the rim of the ship, because the clock is moving sideways very fast, the photon no longer travels vertically, but follows a much longer diagonal path, just like jumping up in a moving bus and landing slightly behind. Because the speed of light cannot exceed c to compensate for this longer path. The time between ticks is longer. The clock runs slower. At the center of the ship, the photon travels almost vertically. The path is short. The clock runs faster. The result is people at the rim age more slowly than people at the center. But the most interesting thing is none of them feels that they are aging slower or faster. Anna at the rim looks at her own clock and sees everything normal. But when she measures Ben's time at the center using light signals, she sees Ben's clock running faster. Ben sees his own clock as normal, but Anna's clock is clearly running slower. And the beautiful truth is, both are correct. No clock is wrong. Each clock is simply honest about the distance. Light must travel in its local frame of reference. When each person lives in their own version of time and is still correct according to the laws of physics, they are forced to seek a more general description to explain these differences. And that is when the concept of a gravitational field appears. From an internal perspective, everything on the ship is exactly the same as if they were living in a real gravitational field. People at the rim feel heavier, as if in strong gravity. People at the center feel lighter, as if in weak gravity. An object released at the rim falls toward the wall of the ship. An object released near the center floats. An object released at an intermediate position falls along a curved path due to the Coriolis force. All these effects, weight, curved trajectories, time dilation, occur without any planet nearby. If the inhabitants of the ship did not know the ship was rotating, they would certainly believe they were living in a real gravitational field. This is Einstein's equivalence principle. You cannot distinguish a real gravitational field from the effects of acceleration if you are confined in a closed system. In the rotating ship, the acceleration gradient with radius creates a time gradient. The farther from the center, the more it resembles a region of strong gravity. That is what allows them to infer that time is not universal, but depends on position within the field they are living in. The real world is not much different. Clocks on the ground run slower than clocks on mountains. Clocks on mountains run slower than clocks on GPS satellites, to the point that GPS must correct time by plus 38 microseconds per day to avoid errors of tens of meters. This proves the truth that the ship's inhabitants accidentally learned. Time is not universal. It is a local quantity. Each position has its own time rate, depending on acceleration or gravitational field. And the similarity between the rotating ship and a real gravitational field is not a coincidence. It is the core of Einstein's idea that gravity is geometry and acceleration is merely another version of that geometry in a non-inertial frame. Once we understand that people at the rim of the rotating ship age more slowly because the photons in their clocks must travel longer paths. We can take one more step and confront a much deeper truth. Time dilation does not come only from velocity, but from the very difference in acceleration within the reference frame. This is the gateway to move from the world of the rotating ship to the world of real gravity. In the rotating ship, centripetal acceleration increases with radius. The farther from the center, the greater the acceleration. That causes time at the rim to flow more slowly than time at the center. But imagine you are an inhabitant of the ship and have absolutely no idea that you are rotating. Then you would describe the phenomenon this way. Time in places where gravity is stronger flows more slowly, because for you the feeling of heaviness at the rim and lightness at the center is not due to rotation. It is due to something that looks very much like a gravitational field, and all the signs point in that direction. The lower someone is in the artificial gravity field, closer to the rim, the greater the acceleration they experience, the slower their clock runs. The higher someone is closer to the center, the smaller the acceleration, the faster their clock runs. That is exactly how time dilation works. In real gravity, going down the gravitational well means going into a region where time is slower. Let's analyze it more deeply with the photon clock. When acceleration increases, the space experienced by the reference frame is stretched in a way that forces the photon to travel a curved or longer diagonal path to reach from one mirror to the other. You can imagine that acceleration makes the floor of space no longer vertical, but tilted at a small angle relative to the photon, forcing the photon to cross a more complicated distance. And because the speed of light never changes, the clock is forced to run slower to ensure it does not violate the fundamental law of the universe. But acceleration does not only change the photon's path, it also changes the energy of the space-time beneath you. The closer to the rim of the ship, the more your reference frame has to resist greater acceleration, meaning the energy required to keep you stationary in the rotating frame is higher. This has profound meaning. Energy and time are directly related. One of the beautiful manifestations of E=mc². In places where more energy is needed to maintain a stationary state, time is naturally stretched more, simply because the photon has to work harder to complete its journey. And when you replace the rotating ship with real gravity, all of this remains exactly the same. In gravity, the acceleration you feel comes from the curvature of space-time. The more curved space-time is, the more the path the photon must travel is bent. Not because space is tilted due to rotation, but because time and space are curved according to the geometry of the gravitational field. Near the surface of Earth, where gravitational potential is lower, the photon must follow a more curved path to complete one tick, so time flows more slowly. On a high mountain, where gravitational potential is higher, the photon travels a straighter path, so time flows faster. This is not empty theory. It has been measured by the Hafele-Keating experiment, by GPS satellites, and by atomic clocks placed at different altitudes. But let's keep digging into the intuition. In a gravitational well, when you move downward, your energy decreases according to the gravitational field. Physics expresses this by saying you are entering a region of lower energy, but time has an energy price in low energy regions. The rate of time flow is different from high energy regions. The equations of general relativity show that the rate of time is directly proportional to the square root of the metric component, a quantity that describes the curvature of time. But you don't need the formula. Just remember that where gravity is strong, the photon clock cells must travel farther, and all time processes are stretched out. In the rotating ship, acceleration increasing with radius causes time to slow down gradually. In real gravity, curvature increasing with depth causes time to slow down gradually. Two phenomena, same essence, Time is affected by acceleration equivalent to gravity. This is the equivalence principle applied at the deepest level. Not only is the feeling of weight the same between acceleration and gravity, the very behavior of time in acceleration and gravity is identical. Imagine two clocks at two different heights. Clock A on the ground, clock B on a GPS satellite, 20,200 kilometers from Earth. Clock B runs faster than clock A by about 38 microseconds per day. This is completely analogous to the rotating ship. The clock at the center runs faster than the clock at the rim. Both are manifestations of one unified truth. Acceleration curves time, or more precisely, geodesics in space-time alter the rate of time flow. And this is a crucial transition point. Time dilation is not a side effect of gravity. It is direct evidence that space-time is curved. If time did not change with gravitational depth, you could conclude that space-time is not curved. And if space-time is not curved, then gravity does not exist in Einstein's view. When time dilation appears, it is proof that you are living in a real gravitational field, not an illusion. Once we understand that acceleration differences in the rotating ship lead to time dilation, and that real gravity is merely a deeper version of the same phenomenon, we can return to the most familiar yet most surprising place, Earth. Here, time dilation happens all the time, everywhere, right under your feet, so gently that you never feel it, yet strong enough to force every modern technological system to respectfully obey Einstein's equations. Time on Earth does not flow uniformly. Clocks on the ground, where gravity is stronger, run slower than clocks on mountains, and clocks on mountains run slower than clocks on satellites orbiting Earth. This is not a metaphor, not a hypothesis, but a fact verified by extremely precise experiments. Let's start with something you rely on every day, but may not know is a direct child of general relativity, the GPS system. Each GPS satellite orbits Earth at an altitude of about 20,200 kilometers with a speed of about 3.9 kilometers per s. Under such conditions, two types of time dilation occur simultaneously. One time dilation due to velocity causes clocks on the satellite to run slower than clocks on the ground by about 7 microseconds per day. And two time dilation due to the weaker gravitational field causes clocks on the satellite to run faster than clocks on the ground by about 45 microseconds per day. When these two effects are added together, we get a net discrepancy of plus 38 microseconds per day. It sounds small, 38 millionths of a second, but if you do not correct for it, your GPS will be off by tens of meters each day, and within just 1 week, the error could grow to hundreds of meters. The world of positioning would collapse. Google Maps would lead you into walls. Airplanes would lose their routes, and every satellite navigation system would become completely useless. All modern technology depends on Einstein being right, and right in a painfully precise way. But GPS is not the only place time dilation appears. In the 1970s, the Haffley-Keating experiment took 4 cesium atomic clocks on airplanes flying around the Earth. When the clocks were brought back to the ground and compared with laboratory clocks, they differed exactly as predicted by general relativity and special relativity. Even in 2010, at the University of Colorado, scientists placed 2 atomic clocks just 33 centimeters apart in height, and the higher clock ran faster by about 4 cots 10 Havretes seconds, a difference so tiny it seems absurd, but today's instruments are sensitive enough to detect it. This means if you are lying on the 2nd floor of a house and your friend is lying on the 1st floor, you are living slightly faster than them, an unimaginably tiny amount, but real. You age faster by an infinitesimal fraction, but enough for atomic clocks to measure. This is irrefutable experimental proof that gravity slows the flow of time. And it happens even in the weak gravitational field of Earth. So what is really happening? From the perspective of curved space-time, when you are closer to Earth's surface, you are in a lower region of the gravitational well, where gravitational energy is lower, and where photons in the clock must follow more curved paths. Curved path longer distant, more time flows more slowly. When you climb to a place where gravity is weaker, the photon's path is less curved, so your time flows faster, even though you don't feel it. Because within your own reference frame, every tick is normal. This small difference is enough to change the technological world and confirm the geometric nature of gravity. Your everyday experience is also affected by this, even if you don't realize it. Clocks in satellite communication vehicles, clocks in national infrastructure measurement systems, clocks in global time synchronization networks like NTP, all of them must account for time dilation. If Einstein were wrong, all those systems would collapse within minutes or hours. But Einstein was not wrong. Time dilation is not just a concept on a chalkboard. It reigns in every electronic device you use. It is the submerged part of the technological iceberg that the entire world depends on. And this prepares us for a big leap. If even weak gravity like Earth's can slow time down just a little, what happens in places where gravity is thousands, millions of times stronger? What happens on the surface of a white dwarf, where a teaspoon of matter weighs tons? What happens near a neutron star, where matter density is 10⁴ times that of water? And most importantly, what happens when you approach the edge of a black hole, where space-time is curved so extremely that even light cannot escape? If Earth only gives us a teaspoon of time dilation, those celestial bodies will pour down an entire ocean. Earth only produces a gentle, subtle time dilation, so delicate that you need atomic clocks to detect it. But there are places in the universe where the gravitational field is so strong that time is bent like a ribbon being squeezed tightly by someone. Two of these deep gravitational wells are white dwarfs and neutron stars. These are not just heavy objects. They are the corpses of dead stars, compressed to the point where their material structure no longer resembles anything you've ever seen on Earth. A white dwarf has a mass roughly equal to the sun, but is packed into a sphere only about the size of Earth, with a radius of around 7,000 kilometers. This gives it a density millions of times greater than water. The surface gravity on a white dwarf is so strong that a 70 kilograms person on Earth would weigh about 10 million kilograms standing there. The space-time curvature near the surface of a white dwarf is so large that time flows noticeably slower compared to regions far away from it. If you placed an atomic clock on the surface of a white dwarf and compared it to one several tens of millions of kilometers away, you would see differences of several percent, something completely impossible on Earth. If you lived 1 year on a white dwarf, observers far away might have experienced 1 year and several months. But that is still not the place where time is bent the most. Neutron stars go far beyond anything imaginable. A neutron star is born when a massive star, with a mass between about 8 and 20 times that of the sun, explodes in a supernova and its core collapses catastrophically. The remaining core, heavier than the sun, is crushed into a sphere with a radius of only 10-12 kilometers. A single teaspoon of neutron star material weighs about 1 billion tons. The surface gravity on a neutron star is roughly 200 billion times stronger than Earth's gravity. The space-time curvature near the surface of a neutron star is so extreme that light is bent dramatically. You could see the backside of the star because light from behind is pulled around the surface. In such a deep gravitational well, time dilation becomes a large, obvious, and genuinely perceptible effect if your technology is sophisticated enough. But before diving into that strangeness, remember one thing. Time does not stop. Time only appears to stop when observed from far away. For the person falling into the black hole, time continues normally until nothing is normal anymore. Imagine you are sitting in a spacecraft approaching a black hole with a mass about 10 times that of the sun. This black hole has an event horizon radius of about 30 kilometers, a region of space smaller than a city, yet containing more mass than any planet in the solar system. When you are still very far away, say thousands of kilometers, the black hole's gravity is just a strong pull. Nothing too bizarre yet. Your ship's clock runs normally, and the distant observer's clock runs in agreement. But as you close the distance to a few hundred kilometers, the true face of the black hole begins to reveal itself. Time dilation becomes brutal. If you live 1 hour near the black hole, a distant observer might experience 2 hours. When you are still about 100 kilometers from the event horizon, 1 hour for you might correspond to many days out there. All of this is because the path light must take in the space-time around the black hole is bent so extremely. Recall the photon clock. If the photon must travel a more curved path, time slows down. Near the event horizon, the photon's path is not just curved. To the outside observer, it is almost stretched to infinity. This is why light emitted from your ship, as you approach the event horizon, becomes progressively redder, fainter, and dimmer. The phenomenon known as gravitational redshift. The light is not lost. Its wavelength is simply stretched so much that it no longer carries enough energy for a distant observer to detect. That is how time performs its slowing through light. Each photon emitted is like a cry, saying, "I'm still here." But the universe stretches that cry longer and longer, sparser and sparser, as if you are drifting into a pool of temporal mud. Move one step further, when you are only a few tens of kilometers from the event horizon. Something bizarre happens in the eyes of the distant observer. You begin to move slower. You do not feel yourself slowing. Your clock still ticks normally, but to them, light leaving you struggles more to escape the black hole, and the time between signals stretches longer. You become like a video being played in slow motion, gradually pixelating, then freezing. If you try to send a signal every second, the distant observer receives it every 2 seconds, then 10 seconds, then 1 minute, then 1 hour, and finally, as you reach the event horizon, the time between signals becomes infinite. The outside observer will never see you cross that boundary. In their eyes, you freeze right at the edge of the event horizon, your time standing still forever. But this does not mean your time actually stops. This is a common misunderstanding. For you, the person falling into the black hole, time continues normally. You can look at your watch and see the hands still moving. You can talk, move, even breathe steadily. You feel no freezing of time whatsoever. Only when you look outward do you see the distant world rushing forward, as if fast-forwarded thousands of times. This comes from the very nature of geodesics in curved space-time. Every light path emitted from you must climb an enormous gravitational gradient to reach the observer, and the larger the gradient, the more time is stretched for the distant observer, while for you it remains unaffected. This is the geometric essence of time dilation in an extremely strong gravitational field. To the outside observer, your clock is forced to synchronize with the structure of space-time around the black hole, a structure so curved that every time interval is stretched to infinity. But to you, you are following your own geodesic, where time remains linear and steady. When you cross the event horizon, something extraordinary happens. All paths leading outward disappear, not because you are stuck due to lack of force. You are stuck because the geometry of space-time has restructured itself. In your coordinates, the event horizon is not a wall. It is simply a place where the gravitational field is so strong that every light path curves inward. you can still move forward. But every attempt to send information outward becomes impossible. From far away, light is stretched to infinity, like a rubber band pulled forever without breaking. From close up, light cannot leave you in the direction against the black hole. All of this is because time and space swap roles when crossing the event horizon. In a Schwarzschild black hole, the direction toward the center becomes the inevitable direction of time, meaning you cannot avoid moving toward the center. That is your time direction. And that is why the slowing seen by the distant observer is purely geometric. No one pressed the pause button on your time. There is no demonic force, only space-time curvature, changing so profoundly that the definitions of before and after, inside and outside, no longer resemble normal. Near the event horizon, the space-time metric stretches light paths outward so severely that photons must climb an infinite time hill. No particle can complete that journey, because none can go faster than light. Therefore, from the outside perspective, your time negates the very possibility of transmitting information, and thus appears to stop. But from the inside perspective, nothing stops. You simply continue toward the center of the black hole, where space-time curvature becomes infinite, and all current physical theories break down. So in the movie Interstellar, why did 1 hour for Cooper and Brand equal 7 years on the mother ship? Because they were extremely close to the event horizon of a very massive black hole, where gravitational time dilation becomes horrifying. That is not science fiction. It is an inevitable mathematical consequence. If a black hole makes time appear to nearly stop as you approach the event horizon, then the rotating model we built from the beginning of this story can be pushed to an extreme version to simulate this intuition. A super-rotating ship, a gigantic spinning machine designed to bring the rim speed close to the speed of light. Of course, this is purely a thought experiment, because no material in the 21st century could withstand such stress. But Einstein always said, imagination is more important than knowledge. And here it helps us understand what is happening near a black hole in the most visual, vivid, and graspable way. Imagine a rotating ship with a radius of 1,000 meters, 10 times larger than our previous ship, and we gradually increase the rotation speed until a person at the rim reaches 0.95 c. That is 95% the speed of light. At this speed, a special relativistic effect appears. The Lorentz factor gamma rises to about 3.2 comma, meaning time at the rim flows more than 3 times slower than time at the center. So if Ben at the center counts 3 seconds, Anna at the rim only experiences 1 second. But we don't stop there. Push the speed to 0.99 c. Gamma is then about 7, meaning time at the rim flows 7 times slower. If the person at the center lives 7 minutes, the person at the rim experiences only 1 minute. At 0.999 c, comma gamma reaches about 22. Time at the rim is almost frozen compared to the center. Push further to 0.9999 c. Comma gamma is around 70. Push even more, and gamma can reach hundreds or thousands as we approach the speed of light. At the rim of the ship, time does not completely stop, but it appears to stop to an observer at the center, exactly like how a distant observer, watching an object approach a black hole's event horizon, sees motion slow down, signals become rarer, the image redden, then seem frozen forever at that boundary. In the rotating ship, the person at the rim does not feel their time slowing. Their clock ticks steadily. They can talk, blink, breathe normally. But if the person at the center watches their clock via light signals, they will see a phenomenon extremely familiar from earlier chapters. The clock is time dilated. Each tick must overcome the velocity of the reference frame itself, forcing the photon to travel a longer, more tilted, and slower path compared to the center clock. This is exactly what happens to light signals emitted from an object falling into a black hole, gravitational redshift. At the rim of an extremely fast rotating ship, we have an artificial version of that phenomenon. Light from Anna is stretched, lower in energy, and the signals are delayed. If we mounted a bright digital clock on Anna and let Ben observe it, as rotation speed increases, the numbers flashing on the clock would go from smooth, slow, jerky, frozen in Ben's eyes. Not because the clock is broken, but because space-time in the rotating frame is distorted in the time direction, exactly like in a strong gravitational field. This gives us a profound intuition. The super-rotating ship is a geometric replica of the region near the event horizon. The greater the centripetal acceleration, the closer the linear velocity gets to c, the more time at the rim is stretched according to the gamma factor. Just like when you plunge deeper into a black hole's gravitational well, your time is stretched according to the Schwarzschild metric. Another interesting point, inside the rotating ship, the person at the center continues living normally, with time almost unaffected. This is similar to an observer standing far from a black hole in flat space. Their time flows calmly and steadily, without strong dilation. Meanwhile, the person at the rim, in the near-event horizon version, lives in a severely curved time rate. To them, everything looks normal, but to the person at the center, their time appears nearly stopped. This is an exact replica of the famous paradox. For the person actually falling into the black hole, time flows normally. For the distant observer, their time stops at the event horizon. An extremely fast rotating ship gives us an easy-to-understand geometric picture. At the rim, the photon's trajectory is tilted to an extreme degree. Near a real event horizon, the photon's trajectory is pulled toward the black hole, to the point where escape is nearly impossible. And in both cases, the cause is not some force, but the geometry of space-time, forcing the photon to travel an infinitely long path to send a signal outward. When we push the rotating ship to near light speed, the rim becomes a mathematical and intuitive replica of the region near the event horizon. One extremely strong time slowing, two light signals reddened and stretched, free motion appearing frozen from the inside perspective. And this is the crucial point. Everything in the rotating model comes from acceleration, not from a real gravitational field. That proves the equivalence principle at the deepest level. Every phenomenon near a black hole can be simulated by a sufficiently strong accelerating reference frame. A black hole is not a magical region. It is simply where the geometry of space-time reaches its ultimate extreme. An extremely fast rotating ship brings you to a place where geometry is also maximally distorted by acceleration. And because photons cannot change speed, time must change to maintain consistency. That is the foundation for every image in Interstellar, every Schwarzschild geometry, and every intuition you have when thinking about black holes. You don't need to actually fall into a black hole to understand it. You only need to sit in an imaginary super-rotating ship, gradually accelerate, and watch your own time melt into slower, sparser, and finally frozen motion in the eyes of others. The super-rotating ship shows us that its rim can become an almost perfect replica of the region near the event horizon, where time is stretched to the point of nearly standing still. And from that arises the deepest question of this entire journey. Why is time dilation something that must happen in the universe? Why can't time simply flow uniformly and understandably, the way childish intuition often tells us? Why must it bend, stretch, and change according to speed or gravity? The answer lies in the three foundational pillars of modern physics. Three principles that, once you accept them, make time dilation not just reasonable, but the only possible outcome. 1, the invariance of the speed of light. 2, the equivalence principle. 3, the geometry of space-time. Let's start with the first pillar, the invariance of the speed of light. This is the core statement of special relativity in 1905, Light always travels at 299,792,458 m/s in every reference frame, whether you are at rest or hurtling along at 90% the speed of light. This has been confirmed by countless experiments, from Michelson, Morley in 1887, to modern measurements with femtosecond lasers. But if the speed of light is fixed, then time cannot be fixed. When you move fast, the photon in your clock has to travel a longer path between the two mirrors. Since it cannot go faster than c to compensate for the extra distance, there is only one possible choice. Your time must slow down to keep the speed of light unchanged. If time dilation did not exist, the speed of light would have to vary depending on the observer, breaking the entire structure of modern physics, from Maxwell's equations to the operation of lasers and GPS technology. The universe would lose its own consistency. Now the second pillar, the equivalence principle. Einstein declared that you cannot distinguish an accelerated frame from a gravitational field in a sufficiently small region. If you feel heavier at the rim of the rotating ship, you cannot tell whether it is due to gravity or due to acceleration. The two situations are physically equivalent. Once you accept that, you must also accept that if acceleration slows time, then gravity must also slow time. You cannot have two equivalent reference frames produce two different rates of time. That would immediately violate the equivalence principle. And if the equivalence principle is violated, general relativity collapses from the foundation. Experiment, once again, stands with Einstein. Clocks on the ground run slower than clocks on mountains. Clocks on mountains run slower than clocks on GPS satellites. And the Haffler-Keating experiment proved this by flying atomic clocks around the Earth. If gravity did not cause time dilation, all those results would have to not exist. The real universe has chosen Einstein's side. And the third pillar, the deepest one, is the geometry of space-time. In general relativity, gravity is not an attractive force. It is the curvature of space-time caused by mass and energy. When space-time is curved, straight paths become curved, and time no longer flows uniformly. Recall the photon clock. The more curved space-time is, the longer the path the photon must travel to complete one tick. If time did not slow down to compensate for that curved path, the photon would be forced to exceed the speed of light to finish its journey, something impossible in Einstein's universe. That means time dilation is the mechanism that allows the universe to keep its oath, that no one is allowed to exceed the speed of light. Any change in geometry, whether caused by acceleration in a rotating ship or by real gravity, requires time to restructure itself. Without time dilation, the Schwarzschild equations have no solution. Planetary orbits are no longer stable. Light is not bent. GPS does not work. And the very definition of a clock no longer matches reality. When you combine these three pillars, you arrive at an unavoidable truth. Time dilation is not a quirky side effect. It is an indispensable consequence of a universe that obeys the invariance of the speed of light, the equivalence principle, and the geometry of space-time. Remove time dilation, and the universe becomes self-contradictory in every equation. Keep it, and everything from planetary motion to lasers to GPS to particles and accelerators operates perfectly. Time dilation is not a choice. It is the foundation that guarantees the consistency of the universe. And once we understand that, we are ready to step into a deeper region of the story. If time dilation is mandatory, what happens when we try to resist it, or when we exploit it? What happens when time does not just slow down, but is stretched to the point where it is nearly torn apart? We are approaching the place where classical physics, intuition, and even imagination must step back to make room for the truly strange things in the universe. If time dilation is the inevitable consequence of the three pillars of physics, the invariance of the speed of light, the equivalence principle, and the geometry of space-time, then we can try a fascinating thought experiment. What would happen if time did not slow down in a gravitational field? What would happen if you stood near a black hole or near the surface of a white dwarf and your clock still ran exactly the same as it does far away? What would happen if the photon did not have to travel an extra temporal distance when climbing out of the gravitational well? In other words, what happens if we force the universe to ignore time dilation and operate according to classical intuition? The answer is very short. The universe collapses immediately, not metaphorically, but mathematically. Every equation describing motion, light, and energy becomes self-contradictory. Let's start with the most direct conflict: conservation of energy. When a photon is emitted from the surface of a planet and climbs to a region of weaker gravity, it gradually loses energy. We see this through gravitational redshift. If time did not slow down, meaning the photon does not spend extra time climbing the gravitational well, then it would have to maintain its frequency while still escaping. That would mean the photon automatically gains energy when going down and automatically preserves energy when going up. But where does that energy come from? If a photon can spontaneously increase or preserve its energy, regardless of height, you are breaking the most fundamental rule. Energy is neither created nor destroyed on its own. Time dilation is precisely the mechanism that conserves the energy of a photon in a gravitational field. The slower time is, the lower the frequency becomes in exact proportion. Remove time dilation, and you make the universe violate its own number one principle. Next is light itself. If time does not slow down in gravity, light will not bend. Remember that light is bent around the sun by about 1.75 arc seconds, as measured by Eddington in 1919, confirming general relativity. Why does light bend? Because curved space-time metric makes the geodesic of light curve accordingly. Part of this phenomenon is due to time dilation. Time flowing slower near large mass makes the effective speed of light in the radial direction different. If you eliminate time dilation, you force light to travel in perfectly straight lines in every situation, and that immediately contradicts experimental observation. No time dilation, no light bending, no gravitational lensing, no Einstein ring, no multiple images of distant galaxy, no data matching the hundreds of observations recorded in astrophysics. Next are planetary orbits. Without time dilation, gravity would just be a Newtonian attractive force. But the problem is real planetary orbits do not match the Newtonian model. Mercury precesses by 43 arc seconds per century, and only general relativity with time dilation explains it. Why do orbits need time dilation? Because planets are not pulled by gravity. They follow geodesics in curved space-time. Part of that curvature lies in the time component of the metric. If you remove that time component, the geodesics have the wrong shape. Orbits are wrong. Planets are unstable. The solar system does not exist. Without time dilation, Earth could not maintain its 365-day orbit. The Sun could not keep its planets in stable revolutions as it does today. Binary stars would exchange energy incorrectly. Astronomical bodies would move along wrong curves. All of this leads to one conclusion. The solar system would disintegrate within the first few million years if time did not dilate in gravitational fields. And that is only the surface. If you continue to remove time dilation from Einstein's equations, you will find that the metric no longer has solutions. General relativity becomes meaningless. Maxwell's equations, written on curved space-time, become incompatible. Particles in accelerators would violate conservation laws. when passing through strong field regions. GPS would be off by tens of kilometers per day. Black holes could not exist because the event horizon is a purely temporal structure. No time dilation, no Schwarzschild radius. No Schwarzschild radius, no black holes, no black holes, no celestial bodies playing the role of restructuring galaxies through energy feedback and regulating star formation rates. Even galaxy evolution collapses. In other words, without time dilation, the universe as we know it could not form, could not exist, could not function. This is not a philosophical opinion. It is a mathematical conclusion. Simply remove the time dilation factor from Einstein's metric, and every structure from the smallest to the largest falls apart. That leads us to the unavoidable conclusion. Time dilation is not a side effect. It is the essential foundation that keeps the universe consistent. Without it, the invariance of the speed of light is broken. The equivalence principle is broken. The geometry of space-time is broken. And along with them, the entire Einsteinian universe collapses like a house of cards. And among all the strange consequences of time dilation, there is one popular example that has surprised millions of people by exposing them to relativity without them even realizing it. Interstellar. This is one of the rare moments when Hollywood accidentally or deliberately got the physics so right that you could use an entire scene as a lecture for university students. The most famous scene, where 1 hour on the planet near the black hole equals 7 years on the mothership, is not the product of over-dramatization. It is the direct consequence of the very principles we have discussed from part 1. Until now, the invariance of the speed of light, the equivalence principle, and the geometry of space-time. Let's see what really happens there. The planet that Cooper and Brand land on is located extremely close to a rapidly spinning supermassive black hole named Gargantua. The larger the black hole, the gentler the gravitational gradient, meaning you can exist near the event horizon without being torn apart by tidal forces. That explains why a planet can remain stable in a region where normally nothing could survive. But it is precisely that size that makes the curvature of space-time so extreme that the flow of time is stretched like hot rubber. And that is the key to the 1 hour, 7 years ratio. You place a clock on the planet in a position extremely close to the event horizon. At that point, each tick of the clock must fight against space-time curvature so large that the path of the photon in each tick becomes much longer than in flat space. The photon cannot exceed c to make up the distance. So the only way to keep the laws from breaking is the clock must tick slower. At exactly that location, your time metric is distorted compared to the metric of people on the mothership. And that distortion is quantified by a time dilation factor that can reach up to 60,000 times if the parameters for mass, spin rate, and distance all match. That means if you feel you have experienced 1 hour, people on the mothership may have experienced more than 60,000 hours, about 7 years. This is not exaggeration. These are numbers. Einstein would approve, Kip Thorne calculated, and Hollywood simply used. Interestingly, Interstellar does not use a static Schwarzschild black hole, but a rotating Kerr black hole. This matters because a rotating black hole drags space-time around it, an effect called frame dragging. When a planet orbits in the same direction as the black hole's spin, time is stretched even more than with a static black hole. To put it a bit playfully, the universe is twisting space-time like twisting a towel, and you are trying to keep the tick-tock of your clock steady inside a violently twisted towel. No wonder your time slows down to the point of almost getting stuck. And this is where many viewers think the movie goes too far. How can there be a planet so close to a black hole without being torn apart? The answer lies in the size of Gargantua. A black hole with 100 million solar masses has extremely weak tidal forces at the event horizon compared to much smaller black holes. For comparison, a solar mass black hole would spaghettify you hundreds of kilometers before reaching the horizon. But a supermassive black hole is gentle, allowing you to approach much closer without your body being pulled into spaghetti. So the planet in the movie not being destroyed is realistic, and the extreme time ratio is realistic too. Now let's return to the intuition we built with the super rotating ship. At the rim of an extremely fast rotating ship, time is almost frozen compared to the center. Light signals are stretched. Clocks nearly stop. Every motion appears drawn into an infinite slow motion state. On the planet near Gargantua, exactly the same thing happens, but due to geometry rather than acceleration. The rotating ship and the black hole are two different ways of producing the same effect. Time geodesics bent to resonate with curvature, causing time to be stretched dramatically. You can imagine people on the mothership looking down at the planet the same way the person at the center of the rotating ship looks toward the rim. Signals become rarer, wavelengths redden, images slow down. That is extreme gravitational redshift. Geometry does it all by itself without any Hollywood tricks. At this point you might smile and say, not every day Hollywood gets the physics right, and that's true, but when they do get it right, it's wonderful. Interstellar, thanks to Kip Thorne, used real Einstein equations, run on real supercomputers, to create black hole images so beautiful that even physicists had to admit, yes, that is exactly how it would look. The time ratio in the film is not magic. It is the unavoidable consequence if you place a planet too close to the event horizon of a supermassive black hole. If time can slow down, stretch out, bend, and even nearly stand still, then what really is time? This is the moment the story moves beyond mathematical formulas and touches the very foundation of our perception of the universe. From the moment we are born, we are accustomed to thinking of time as a steady, fair, continuous flow, like the universal wall clock of the cosmos. But time dilation shatters that intuition. It says time is not absolute. It is not a common quantity for every place and every person. Time is your time, measured by clocks in your reference frame, affected by the speed you move at and the gravity you are in. If you live near the surface of a white dwarf, you will age more slowly than someone living in deep space. If you live on a ship rotating near the speed of light, you could experience an entire lifetime in what is only a single beat of the universe. Time is no longer a backdrop. It becomes a physical field, something that can be acted upon, bent, deformed. From a philosophical point of view, this makes familiar questions suddenly profoundly deep. What is the true lifespan of a human being? If two people are born at the same moment, one living on Earth and one living in a stronger gravitational field, they are no longer the same age after a long time, even if both measure 80 years according to their own clocks. But which of them is really older? We can say that neither is really older, because there is no common time rhythm to compare against. Each lives in their own time, what Einstein called proper time. This is not just science. It is the shattering of one of humanity's most fundamental illusions, the illusion that time is an absolute straight line, that every creature walks along together. Another philosophical consequence is the way humans view the universe completely changes once they understand time dilation. Before, we thought the universe is vast, but its age is legitimate, 13.8 billion years for everyone. But in reality, the age of the universe depends on your position in space-time. A person living near an extremely large black hole might experience only a few million years, while the rest of the universe has aged billions more years. The same universe, but many different versions of time. This leads to a profound shift in perception. The universe does not have a single timeline that everything follows. The universe has countless timelines, each one a geodesic of existence for a system, a person, a particle. They are not synchronized. They only interact through light and geometry. Time becomes something produced by paths through space-time, rather than the stage on which everything takes place. And if that is the case, old philosophical questions need to be rewritten. Now is not a common 3D surface across the entire universe. Your present may be someone else's past and a third person's future. Simultaneity, the idea that two events can happen at the same time, is no longer absolute. Even if you ask, at what moment is the universe happening, that question loses meaning. Time dilation does not just change physics, it changes the way we understand existence. It says that lifespan is not an absolute number, but a path through space-time. It says that the universe does not flow. We flow within the universe. It says that time does not pass us by. We move through time like a route curved by gravity and velocity. Most importantly, it says that every creature, every planet, every particle lives in its own private world of time that no one else can replace. There is no cosmic clock, only local clocks, each telling its own story of experience in this curved universe. When we understand that, the universe becomes wider, deeper, and more beautiful, because it does not merely give us space to exist, but also gives us infinite ways to experience time. And it is precisely within that infinite diversity of timelines that humans truly see themselves as small yet genuinely free. Once the philosophical implications of time dilation have sunk in, someone is bound to ask, so can I exploit time dilation to live longer, or even escape aging? It sounds reasonable. If time slows down near a black hole, if an astronaut moving close to the speed of light ages more slowly than people on Earth, then why don't we build a super-fast ship or move to live near a gentle neutron star to extend our lifespan? The short answer is, in theory, yes, but in reality, no. Unless you enjoy being stretched into spaghetti, being heated to billions of degrees, or being crushed into plasma. Time dilation is not a cosmic spa where you lie down and premium. Slow time service is provided just for you. Time dilation always comes hand in hand with physical conditions so extreme that your body and every piece of technology you have cannot survive them. Let's try the first option, traveling near the speed of light. To achieve gamma equals sine 2, meaning you experience 1 year, while Earth experiences 2 years, you need a speed of about 0.866 c. Want gamma equals sine 10, your speed must be 0.995 c. Gamma equals sine 100, you need 0.9995 c. These numbers are not just challenges, they are energy death sentences. To accelerate a 100-ton ship to 0.99 c, you would need energy equivalent to many months of total human electricity production. To maintain that speed in space, you would have to deal with interstellar dust particles hitting the ship like fragmentation bombs. A tiny grain of sand colliding with a ship traveling at 0.99 c would release energy comparable to a large bomb. You are not escaping aging. You are turning yourself into a relativistic fireworks target. Now the second option, living near an object with strong gravity, where time runs slower. It sounds simple. Go deep into the gravitational well, and you will age slowly. But let's revisit the earlier calculations. The surface of a white dwarf has gravity so strong that you would be compressed into a thin sheet like paper. The surface of a neutron star has gravity 200 billion times stronger than Earth's, and temperatures of millions of degrees. You wouldn't have time to escape aging. You would escape existence. What about a black hole? There is no near a black hole that is safe unless it is a supermassive black hole, and you are flying on exactly the right stable orbit. But even then, tidal forces would gradually stretch you apart as you got too close, killing you long before you could enjoy the benefit of extended lifespan. And even if you found a safe, stable orbit, something rare in extreme gravitational fields, you would have to carry enough food, oxygen, supplies, for decades with no possibility of resupply. You might live longer according to your own clock, but according to everyone else's clock, you would simply disappear. The harsh reality is time dilation is not designed for life extension. It only works as a one-way trip into the future, but not in the romantic Hollywood way. You cannot come back. You cannot reverse aging. You can only experience less time than others during an extremely dangerous, extremely expensive, and extremely biologically unsuitable journey. It is like saying, I want to live longer by jumping into a tornado. In theory, possible. In practice, you get torn to pieces. And here is the key point. Time dilation is not a tool for escaping aging. It is merely the difference in time experience between reference frames. It does not change biological structure, does not rejuvenate cells, does not prevent cancer, does not cure disease. It only changes how many years you experience relative to others. That means you can travel into the future by going fast or living in strong gravity, but you will not live longer in the sense you desire. You are simply skipping over a portion of other people's time, and even that path comes with terrifying danger. Time dilation is one of the beautiful parts of the universe, but it is not an anti-aging solution, not a secret to immortality, not a shortcut to escape death. It is simply a fact. Time is not fixed, and you cannot control it to serve personal purposes without paying a brutal physical price. It is precisely from the fact that you cannot use time dilation to escape aging that we see a deeper principle every physicist eventually learns after spending long enough talking to the universe. There is no free lunch in nature. You want time to slow down. Fine. But you must accept traveling near the speed of light and pay with astronomical amounts of energy that no current civilization can provide. You want to jump into an extremely strong gravity region to live longer. Fine. But you must accept being stretched, incinerated, crushed, or falling into a geometry where every timeline leads to a single point called the singularity. Nature never says no, but it always says yes with conditions. And those conditions are usually so brutal that 99.99% of all creatures in the universe would never dare pay the price. This brings us to a broader perspective on how the universe operates. When first encountering relativity, many people feel as though Einstein unlocked the magic box. Time slows down, light bends, space-time stretches, black holes swallow the future. But the deeper you dig, the more you realize none of it is magic. It is all the logical, consistent outcome of the three pillars we discussed: the invariance of the speed of light, the equivalence principle, and the geometry of space-time. Once you accept those three things, the universe doesn't have much left to decide. It must curve here, bend there, slow time in this region, speed it up in that region, just to keep every equation from contradicting itself. And everything that looks miraculous turns out to be nothing more than mathematics being honest with itself. Consider the classic example. You want to move extremely fast. Fine. But your time must slow down to preserve the invariance of the speed of light. You want to keep time running normally while going fast. Not allowed. You just broke the foundation of electromagnetism and relativity. You want to stand near a black hole and still live as long as usual. Fine. But you must find exactly the right kind of supermassive black hole, the right safe orbit, the right spin rate. And even then, outside time will race ahead thousands of times faster than you. You live longer, but the world you knew will age in the blink of an eye. You want to exploit strong gravity to extend biological lifespan. On paper, yes, but the gravity is so strong, it instantly destroys every atomic structure in your body before you even realize you were living longer. In every scenario, what you want to achieve must be traded for something else. There is no case where you get the whole world without losing anything. Nature does not need to be reasonable to us. We must be reasonable to nature. The universe does not construct its laws to suit human intuition. No one asked us whether we feel comfortable with time stretching. No one cares that we prefer to imagine time as an absolute straight line. The universe operates according to its own principles, not our emotions. And every miraculous effect, from time dilation, redshift, black holes, wormholes, to gravitational waves, is simply the inevitable consequence of nature staying faithful to its own foundational rules. Notice the elegance of the universe lies in this. It allows almost everything, as long as you pay the corresponding price. Want to bend light? Fine. Need large mass. Want to change the flow of time? Fine. Need absurd amounts of energy. Want to reach the future faster than others? Fine. But you cannot return. Want to travel near the event horizon? Fine. But you must accept never sending any signal outward. All of this shows us a universe that is not cruel, but merely consistent. It does not punish you for wanting to do strange things. It simply demands that you pay the appropriate physical price. And it is precisely because of that consistency that the universe becomes astonishingly beautiful. No hidden rules, no secret exceptions, no VIP user privileges, just geometry, energy, and velocity, together with their inevitable consequences. Once we see that the universe never gives anything for free, that every strange effect must be paid for with energy, geometry, or physical limits, we finally arrive at the deepest conclusion of this entire journey. Time dilation is not a side effect, not a decorative detail in Einstein's theory, not something that happens when you go fast or stay near strong gravity. It is one of the foundational pillars that the entire universe rests upon to exist. Without time dilation, you do not just lose a few pretty effects in physics lectures. You lose the entire ability of the universe to function. Without it, the speed of light cannot be invariant. Without it, the equivalence principle cannot hold. Without it, the geometry of space-time cannot work. Without it, Einstein's equations have no solutions. Without it, planetary orbits are unstable. Without it, every photon violates energy conservation when passing through a gravitational field. Without it, light does not bend. Mercury does not precess. GPS does not work. And the universe has no way to maintain consistency between motion, energy, and geometry. Time dilation is the piece that keeps everything fitting together. Look back at everything we have covered from the beginning. In the rotating ship, time slows because the photon must travel a longer diagonal path. On Earth, time slows because gravitational potential is lower. On white dwarfs and neutron stars, time slows dramatically because space-time curvature is enormous. Near black holes, time nearly stops because geometry forces photons onto geometrically infinite paths. In interstellar, 1 hour equals 7 years because the planet sits right next to a gravitational field that general relativity predicts exactly. None of those examples are disconnected pieces. They are different manifestations of a single principle. The universe always adjusts time to ensure the speed of light remains unchanged, and every geodesic in space-time remains mathematically consistent. In other words, time dilation is the mechanism the universe uses to avoid breaking itself. It is the shock absorber of space-time. The tool geometry uses to balance every distortion caused by motion or gravity. Without time dilation, you could not define a clock. You could not define the path light travels. You could not describe planets orbiting stars. In fact, even the concepts of day, year, heartbeat, age would not exist. And the deeper you look, the clearer one majestic truth becomes. Time dilation is what allows the universe to have structure. Without it, light would not follow the curved paths necessary to produce gravity. Every star would eject matter instead of holding it. Galaxies could not form or maintain their shape. Gas clouds could not collapse into stars. The solar system could not be stable. And if the solar system is not stable, Earth could never maintain an orbit durable enough to allow life for billions of years. Without time dilation, there is no life in any sense we understand. From the first bacteria to humans, every living thing requires a stable geometry, stable temperature, stable orbit, stable energy, and all of those depend on equations that time dilation keeps consistent. It is not something to play with, not a tool for movies, not an effect to show off CGI technology. It is the deep heartbeat of the universe, the thing that allows everything from the tiniest photon to gigantic spiral galaxies to operate according to laws that do not contradict themselves. When we say without time dilation, we would have nothing, that is not exaggeration. It is an accurate description of the mathematical structure of the universe. Remove time dilation, and everything from the smallest to the largest collapses. Keep time dilation, and we have the beautiful universe we live in. And the most wonderful thing is relativity does not ask you to believe in it. It only asks you to observe. When you look at GPS, you see time dilation. When you look at light bent by distant galaxies, you see time dilation. When you look at neutron stars, black holes, Miller's planet in Interstellar, you see time dilation. Every observation points in one direction. The universe is built on a foundation of non-absolute time. And if you understand this, you do not just understand one physical effect. You understand a piece of the soul of the universe. It does not force time. It allows time to bend itself according to its own geometry. Time dilation is how the universe keeps its promise to Einstein, a consistent, beautiful, intuition-challenging universe, where everything happens exactly as nature wants, not as we wish. If you truly understand something, try explaining it to someone else. This is not a study trick. It is how the human brain reveals truth. When you try to articulate a difficult idea, like time dilation, for example, you immediately discover the parts where you are still vague, the links that are still loose, the sections you thought you had mastered, but actually only sound familiar, rather than truly understood. That is the method I have used my whole life to teach physics, to learn physics, and to test whether I really understand what I am talking about. And I am serious. After hearing this entire story, do not let it just sit quietly in your head. Find a friend, a colleague, a student, or even a cat. Cats won't understand, but they won't complain. And try explaining it again. Tell it in your own way. Why does time slow down? Why does a black hole make it nearly stop? Why isn't Interstellar made up? Why does the universe need time dilation to avoid collapsing? See if you can put the pieces together into a coherent story. If you finish, and the listener says, "Oh, so it's actually easy to understand," congratulations, you have passed the biggest test. And if they get confused, or you get confused, or both of you get confused, even better. The universe was not created for us to understand in one afternoon. You have to peel back the layers, ask every question, and be patient with yourself. Science does not reward the fast. Science rewards the persistent. And do not forget one thing I always like to remind people. Understanding the universe is already beautiful enough. You do not need to add magic to make it more magnificent. Gravity does not need to be mystical. Time does not need to be sacred. They just need to be correct. And this universe in its own way is already a miracle precisely because it follows laws that our small minds can understand. So this is my farewell to you. Keep being curious. Keep asking questions. Keep doubting. And the next time you meet someone who says time is absolute, or gravity is a pulling force, or interstellar is all made up, just smile and say, let me explain it to you. Because the moment you start explaining is the moment you truly understand. And if you manage to do it, congratulations, you have just completed the Feynman challenge. If you enjoyed this journey of discovery, please subscribe so we can continue exploring the universe together in a fun and clear way. See you again in the next adventure, where countless more wonders are waiting to be explained.